Hello again. Welcome back to Engineering 211 Statics. Last time we were talking about moments in 3D and using the cross product, and I wanted to continue on with that with some examples today. So we'll get right into it. This first example, we've got something, maybe this is a column or a post, and it's got a rope or cable attached at the top up here, and we have this person applying a force through that rope or cable of 20 newtons. The column itself is 10.5 meters in height, and this person is standing on the XY plane, as you can see, standing on the XY plane at a location of 3 meters in the minus Y direction and 4 meters in the positive X direction. And their feet are here on the XY plane, but they are pulling at chest high or something like that. So the end of this rope actually does not terminate at the XY plane, but 1.5 meters above the XY plane. So that's important to note. So what we'd like to do is we'd like to find the moment about O, the moment that is created about this point here. So let's see if we can do that. There are a couple of ways that we could go about this. Let's put this as point A so we can talk about this, and then we will say that down here this person is point B. So we could say that the moment about O is equal to over here, the moment about O is equal to the position vector from O to B. So right there, R from O to B, R from O to B, crossed with the force F. So we're going to have to spend some time quantifying what F is here. Going back and remember, we can write F as its magnitude times the position vector from A to B divided by the magnitude of that position vector. So let's see how that works out. We know that it has a magnitude of 20 newtons. And then I need to multiply. How do I get from A to B? Imagine giving yourself instructions. You'd have to go 4 in the I direction, minus 3 in the J direction, and then minus 3 in the J, and then minus, not 10.5, but we're only going to go down 9 because this is 1.5. This is 10.5 above the XY, and this is 1.5 above the XY, so we'll subtract 9, the difference between 10.5 and 1.5 in the K direction. So does that make sense? We come down here, 9 minus 9, then we have to go minus 3, and then we have to go out 4. Hopefully that works out. So we then divide this by the square root of 4 squared plus a minus 3 squared, which would be we'll just say 3 since the negative goes away, plus 9 squared because the negative would go away there. When you get done with this, when the smoke clears from all this math, you have 7.77 in the I direction, minus 5.83 in the J direction, minus 17.5 in the K direction. That would be newtons. Let me double check that. 7.77, 5.83 minus, yes, 17.5. So that's our F. And then we were going to do this crossing. So how can I get this find this R from O to B? So if I wanted to get R from O to B, what's that going to look like? Well, how do I go from O out to B? That would look something like this, wouldn't it? I'd have to go 4 in the X, minus 3 in the J, and then remember that would put you at the feet of this person, so you're going to have to go plus 1.5 in the K. So out 4, back 3, and then up 1.5. So when you cross this, this is going to look then like ROB crossed with F would be equal to you have to put in the R first. The order is important. 4 minus 3 1.5. And then you're going to have this one, 7.77 minus 5.83 and minus 17.5. Okay, minus 17.5. That's a little bit awkward there. Let me try and clean this up. Get a little better pen here. We got a clean pen for that. So 7.77 in the I minus 5.83 and minus 17.5. Okay, and again, that's a little clear. It should show up well on the PDFs if you're having a hard time seeing it on the video. Well, when you do that crossing, let's see what you come up with. You're going to come up with going through this. You could, you can go through, look at the last video that I did, and it talks about the mechanics of going through and doing this cross product. Or once you're comfortable with that, you can put it in your calculator and speed up the process. But you're going to have 61.2 in the I direction plus 81.6 in the J direction, and that would be Newton meters. Okay, Newton meters. So there's actually no Z component, so only an I and a J component. So we could take that as our answer if we wanted to, 61.2 in the I plus 81.6 in the J. We could also, if we wanted to, look at this a little differently. That was our R vector. We could also take an R that goes from O to A. What about that? Yeah, we might try this. Say that the moment about O would be equal to R from O to A crossed with F. What's that look like? Well, R from O to A should be pretty easy to do, and that's probably one advantage to this one. What's that going to be? That's simply just 10.5 in the K direction. So I could rewrite this as I, J, and K. Then we have 0, 0, and 10.5. And then I still have F. I still had to go through and find that. There's no avoiding that. 7.77 minus 5.83 and minus 17.5. So when you go through that, you go through the cross product. This turns out to be 61.2 in the I direction plus 81.6 in the J direction, 0K, and that'll be Newton meters. You get the same answer. So that's really why I wanted to do this problem, is to illustrate you could use this R or you could use this R. If you wanted to, you could look at the line of action of this thing and come back and maybe select an R that was clear up there. That R would work. Or you could use this R here. Now, unless you know this point and you know this point, that's probably not a good choice, but you can use those R's anywhere on that vector or on the line of action of that vector. So that's an important point, and one that's hopefully illustrated well with this problem. Well, let's move on then, continue to work problems that will hopefully give us practice and illustrate some points like that. The next thing I should probably take a little moment is what if we want to find about the moment through a particular axis? So we can talk about the moment of any axis. We'll call that lambda through O. Okay, can be written as time about lambda is equal to the unit vector for lambda. So we have the unit vector for that axis dotted with r crossed with f. So what we're doing here, this is of course the unit vector for lambda, is if I want to find out what the moment in a particular direction is or on a particular axis, I take the unit vector for that direction or axis and I dot it with the moment that we calculated. Okay, fairly straightforward. I mean, going back to our previous problem, if I wanted to know the component of this in the I direction, I just dot it with the unit vector in the I direction and I'd get this piece. If I wanted to know the component in the j, I'd dot it with the unit vector and I would get that piece there. Make sure I get those right. Double check that again. Yeah. So hopefully fairly straightforward. Now, if I wanted to get it in some odd axis, I would just find the unit vector for that odd axis or direction and dot it with that. One thing before leaving this is probably worth looking at. Go back here, apologize for this, hopping back to this problem, but looking at these answers here, what does that really mean? I go 61.2 in the I, so there's 61.2 in the I, so I'm going to come out like this, and then 81.6 in the j, so 61.2, 81.6, there is where our moment is, okay, like that. And those of you that have maybe cut down a tree or been around logging operations or seeing pictures of this, they usually, as they cut it down, they have some hinge wood. If you see this tree as you cut this down, I apologize to people that don't like to cut trees down, but if you want it to roll over like this, you're going to come in and cut this out and then make a back cut like that. Usually they'll cut down because they want to leave that on the stump and not the tree. But you have this piece of wood that's left in here, right through here, what we call the hinge wood, and that's what it rotates around. And you could think about this, if this person were to pull hard enough on this, that it would rotate around this axis right here, and that would be the hinge. And in fact, you could extend and think about it rotating around that. So that's kind of what that answer represents. Well, if we wanted to take this answer and we wanted to find its component in this direction or that direction, it would be a simple matter of dotting it with the unit vector for that direction. That's what we're getting at with the next step. And for that matter, if we wanted to find its direction along this line out here, we could do that also. We just have to find the unit vector for that line. So there's nothing particularly magical about this. We're just dotting it with a direction that we're interested in finding the component along. Now this has kind of an interesting name. If we take R and we cross it with F and then we dot it with the unit vector, this is defined, and you probably see this in your math book, as a triple scalar product. Which is kind of interesting. Of course, when you do the cross, you end up with a vector when you cross something. Again, going back to this previous example, we crossed, we got a vector for our answer. But then when you dot it, you end up with a scalar. So we have this triple scalar product. So whether you remember the triple scalar product and that kind of terminology, you can still use these concepts. Let's try it in a problem then. So we're back here, page 3. So let's try this thing. We've again got a column that's 15 feet high. It is 9 feet into the z and 12 feet in the x. So we've got the xz plane down here. Rotated coordinates, but again, this is a right-hand coordinate system, so I think we're okay. We've got this guy wire that has a tension of 10 pounds going from the top of this column at A down to this point on the xz plane at B. And what we'd like to do is we'd like to find the moment about the z-axis. Presumably, there's some rotational sense about the z-axis, and we'd like to find what that is. So let's see if we can do this. If I were to talk about the, which do we want to do? Well, we know if we find the moment about O, the first thing I want to do, if I find the moment about O, I could say that's equal to some R crossed with the tension. We'll just use the variable T. So that's our force, and that's our R. Which R should we use? Well, probably a pretty easy one is from O to A, wouldn't it? So we'll go from O to A, and we will cross it with that T. So let's come up with the ingredients here, the pieces. R from O to A is going to be what? I just go 15 in the J direction, because J is the Y direction, so I'm going to say 15 in the J direction. And then if I look at T, I know it's the magnitude of T, which we were told was 10 pounds. Then the position vector, how do I get from A to B? I would have to go 12 in the I direction, minus 15 in the J direction, and then plus 9 in the K direction. Let me then divide by that magnitude, the square root of 12 squared plus 15 squared plus 9 squared. The negatives go away when you square it. Now, does that work? Let's see. If I go from A to B, I'm going to go minus 15 in the Y. Yep. I'm going to then have to go 9 in the Z. Yep. And then I've got to go 12 in the X. So yes, that's correct. And that turns out to give us an answer that is 5.65 in the I, minus 7.07 in the J, plus 4.24 in the K. So 5.65 in the I, minus 7.07 in the J, plus 4.24 in the K. So we can say then, if we do that crossing, that the moment about O is going to be equal to, we put that into our vector form, I, J, K, or crossing form. We're going to have what? 0, 15, and 0. That's what that looks like. And then 5.65, squeeze this in here. And minus 7.07 and 4.24. Okay. And there's a couple ways. I mean, you could say it was this, or you could actually just say that you had 15 in the J, and you're going to cross that with 5.65 in the I, minus 7.07 in the J, plus 4.24 in the K. Okay, so we would have, then going through this, 15 times 5.65, and that would be J crossed with I. What is J crossed with I? Again, I always go back and look at I, J, K. So J crossed with I is what? Minus K. And then I have 15. I guess I'll write this out. I don't think we've done this before, so maybe I'll write this out. 15 times a minus 7.07, and then what is J crossed with J? That's 0, isn't it? So that one will go away, and I will have then 15 times 4.24, and J crossed with K gives me I, doesn't it? Okay, so when we tidy this up, we've got minus 84.7, 84.7 in the K direction, plus 63.6 in the I direction. I don't have those in proper order, but I think we're okay that far. Let me double check that first term. Yep, good. Okay, So whether you go through this process, or if I have a lot of zeros in one of these vectors, then a lot of times I'll just do it this way. I wanted to go through that so you could see where that came from. So now we're not done yet. This is the moment about O. If we wanted to name this, there is the moment about O. We need to put units and whatnot on it, but we're not done. I want the moment about Z, so I can get that. Oops. There we go. So this will be 4. So as we continue on here then, we could say that the moment about the Z would be equal to the moment about O dotted with the unit vector for the Z direction. So I could take minus 84.7 in the K plus 63.6 in the I and dot that with, so this is dot that with what? What's the unit vector in the Z direction? That's 1 in the K, isn't it? So that's really just going to give me minus 84.7 in the well, in the K, minus 84.7. That's going to be, we had what? Pounds and feet, right? We're up here. This is feet. This is pounds. So I had pound feet. Okay, so that would be our answer. And with this triple scalar here, I kind of made a big deal. Most people will just look at that and say, well, hey, that's the Z component right there, and that matches our answer. Now, if they wanted to know it about, instead of on the Z axis here, they wanted to know about some line somewhere, then you'd have to find the unit vector for that, and probably this would be a bit more useful. So pretty straightforward. You go ahead and find the moment about a point, and then dot it with the unit vector for the direction that you're trying to find the component of. Okay, I guess the last thing is we might again look at this. What does this answer mean, the moment about O? I go minus 84.7 in the K direction, so I'm going to have to go way back here, aren't I? There's minus 80.4.7, 63.6 in the I, so there is 63.6 in the I, and I will then have that as the moment about O, which again, if you look at pulling on this thing, it's going to rotate essentially about an axis, or even you could think of it as an axle along that axis. So hopefully you can rationalize that intermediate step and make sense of that. Well, one more problem that I'd like to look at for today or for this lecture. And again, I encourage you, as you go through your reading, do the example problems through the text. A lot of times I'll just grab an old textbook and flop a problem up here, and that's some of the ones that we're working on. Different textbook, different authors, but if you see the problem in the reading and it has the solutions, or a problem in the back of the chapter and it has the solutions, that's a great one to try. I mean, the only reason I'm saying it has the solutions is so you can check to see if your answer's right or wrong. So I encourage you, as you go through your reading and go through your author's work, check on those problems as you go. Well, this problem here, we've got a scenario. Let me grab a, probably should get a little better. Okay, there we go. There's a good one. So we have a scenario here. Maybe this plane, this YZ plane, represents a wall or something like that, and we have a door or maybe a window. You could think of a window that rotates around some hinges. So you have a hinge here and a hinge here and a hinge here along this line BC, and this window rotates out. And we're going to open this window by applying a force here of 200 newtons. I guess it's a metric window, whatever that means, but 200 newtons. And that 200 newtons is at an angle of 60 degrees with respect to this y-axis, and it is in the xy plane. So this 200 newtons is in this xy plane here. The height of the window is 0.3 meters, and the length or width of it is 0.5 meters. And what we'd like to do is we'd like to find the moment about BC, because the other pieces of the moment aren't going to go to opening it. The only one that helps open it is this moment that goes around there, right? Okay, so I'm going to do this a couple different ways. I'm going to do it in a approach that we'll use the scalar pieces, and then we'll try it again with the vector pieces. So if I break this up, if I talk about fx, that's the component in the x direction, that's going to be what? That's going to be this side over here, isn't it, of that triangle, which would be equal to 200 times the sine of 60, opposite, so I have sine of 60, which gives me 173 newtons. And if I wanted to talk about Fy, let's see, Fx, that's positive, right? And there's Fy, that's that piece out there. So that would be 200 times the cosine of 60, which is equal to 100 newtons. And I should probably note that this is in the negative y direction. It's going that way, negative y direction. Just so we remember that. I won't put a negative sign on it because I could represent with that with the arrow, but we'll keep track of that a little more carefully. So if I want the moment about BC, I could really just say that the magnitude of the moment about BC is equal to this force Fy has no bearing on that because that's parallel to BC. So I really just say that it's the x component, force x, times the distance from, let's say, C to A, which is going to be equal to this number here, 173 newtons, times the distance of what, 0.3? Is that right? 200 sine 60, yeah. So that turns out to be, I think, 52. Let me double check that. Yep, 52. So I've got 52 Newton meters. So that's the magnitude. And I think you can recognize if you've got this force here, there is essentially your Fx, right? That this is going to rotate. I haven't done a very good job on this arrow. Let me change this up a little bit. I'll make this a solid line. It's a little bit hard to see. Sometimes you have to squint one eye and close the other. But that's going to be coming around like that, isn't it? Okay, it's going to be going into the paper above this and out of the paper below it. So if I were to look at this with a right hand rule and take my right hand, put my fingers in the direction of that arrow, it's going like that. My thumb is pointing in what? The minus y direction, isn't it? So use the right hand rule to get that the moment about BC is equal to 52 in the minus, what's the minus y direction? That's minus j, isn't it? So I have minus j, and that would be Newton meters. Okay, so I went from this magnitude here, and knowing it was going that direction, using the right hand rule, putting my fingers in the direction of that rotation, and my thumb points in the minus y direction. This is a minus y direction. So minus 52 in the j direction, negative because the minus y direction. Well, a couple points that you might hang up on is what happened to this Fy. Well, this Fy is actually parallel to that and doesn't change it at all. For instance, if you had, let's say, a doorway. Let's say you look at a door. Everyone's got a door at home, and you look at the door here. There's the doorknob, and you've got hinges, probably 3 of them. If you apply a force like that, that's going to open or close the door. It's going to rotate it around that axis. Whereas if you hang your coat on the corner of the door, Okay, or you hang on the door or something like that. If you apply this force there, does that open or close the door? Certainly it does not. So it's parallel with this axis and causes no moment around that axis. So that's why we got to ignore the y piece here. Well, if our right-hand rule and whatnot didn't make a lot of sense, let's try this with a vector approach. So I'm going to come up with some pieces here. I'm going to come up with a unit vector for the BC. And I'm going to say that's equal to 1 in the j direction. So there is UBC, 1 in the j direction. So I've just taken it going to the right. I'm going to talk about RA as being equal to minus 0.3 in the k direction. Where did I get that? Well, I went from this line to point A. So right there is RA. And finally, the force, I could say, was equal to, and I'll quantify the force. I'm going to have 173 in the x, so that'll be the I, minus 100 in the j. So I've got the x piece here, I've got the y piece here, and remember that's in the negative y direction, so I've represented that with a negative sign there. So now when I say RA crossed with F, so that's the cross product, and that's going to be equal to what? You could put it into an array if you wanted to, or this might be just as easy. I'm going to have this, so minus 0.3 times 173, and that's going to be then k crossed with I. What's k crossed with I? That's positive j, isn't it? Okay, and then I've got to add to that a minus 0.3 times a minus 100, and what is k crossed with j? That's minus I, isn't it? Okay, and if you're more comfortable doing it in this form, I, j, k, you're going to have 0, 0, minus 0.3, and then 173 minus 100 and 0. That's fine. Throw it in your calculator. You should get exactly the same answer. But when you hammer this out, you come up with minus 30 in the let's see, I'm switching on you here, aren't I? This is going to be negative, and a negative, and a negative gives me a minus 30 in the I direction, and then this is one negative, so it gives me a minus 0.3 times 173 gives me 51.9, or we could call that 52 in the J. Okay. So minus 30 in the I, minus 51.9 or 52 in the J. So now what I'm going to do with this thing is I'm going to take this, I've got I think just enough room here, and say the unit vector for BC dotted with this thing, minus 30 in the I, minus 52 in the J, gives me what? Well, there's your unit vector right there. It just says to take the j term, essentially. So you're going to have minus 52. You just get the magnitude out. Minus 52, and that will be Newton meters. Okay, so that's in the about the axes BC. So I think we're okay there. We got the same answer. Whether you want to do it with the two-dimensional approach or the three-dimensional, certain problems are going to definitely lend themselves to one or the other. If this was a problem where this window was skewed into the some of it was in the x-plane and the z-plane, then probably this last method would be a lot easier. But it's always nice to, if you can, do it with a couple different methods and be able to confirm, make sure that you get the same answer. So we got the same answer. I think we are in pretty good shape there. Well, I think that's all of the problems that I wanted to do for this lecture. When we get together on the next lecture, we'll talk about a special type of a moment that's created by two equal and opposite forces. We will call that a couple, and we'll go on from there. Thank you for watching, and take care till then.